that others who may have missed out on today's events will be able to come and watch it. So thank you. So now at this time, please mute your mics for best sound experience. Otherwise, the feedback could interfere with information we will be sharing today. We will be sending the 1324 room link on the chat so that you can connect to your session if you are here for Math 1324. Without further ado, I will pass it on to our presenters so that we can begin. Thank you.
Well, good afternoon, everyone, and yes, happy Friday, right? I hope everybody's having a good end of the week, and we thank you all for joining us for this math happy hour. So we'll give a couple of seconds for those who are, again, joining us to do review for Math 1324. Please click on the link that you'll find on your chat. Very good. So let's go ahead and get started. So for today's session, we're going to be looking at the standard form of quadratic equations and graphing. Again, if you have any questions, please feel free to raise your hand or put it on the chat, and we will get to them. Okay. So let's go ahead and start by defining what the standard form of a quadratic equation is. So the first equation is the new equation that we're going to be seeing that hopefully you've seen already in your classes, which is what I consider or call the general form, right? It's ax squared plus bx plus c. The second equation, well, we saw that one before, and that one's the one that's called the standard form of the quadratic equation. And we like to call it the standard form because just by looking at it, we're able to define what our vertex is. Yes? So let's go ahead and do the definition of the quadratic function. The quadratic function is a function here that our highest exponent, or the degree of the polynomial here, is a 2. Okay? So the graph is represented by a U shape called a parabola. And if we look here at our parent function, f of x is equal to x squared, again, our parabola is a positive, so it's pointing up. It has a vertex at the origin at 0, 0. Again, we know that quadratics are polynomial functions with a degree 2. The degree is the highest exponent number that a polynomial has, and in our case, all quadratic functions are going to have a degree of 2. Okay. All right, so let's look at a little bit of information as far as when graphing. If we look at our general form of our quadratic equation, if our a value, again, is a positive value, this is going to tell us that our parabola is pointing upward. If our a value is a negative value, we know that it's going to be reflected on the x-axis, so our parabola is going to be pointing downward. So thank you, Ms. Chuka, for those arrows. Okay. All right. So again, if we have the the quadratic in general form, it's very hard for us to really look or get a sense of what the graph looks like. But when we have it in standard form, which is in this form, a times x minus a squared plus k, where h and k represent our vertex, in this case, we're able to see that, again, what our vertex is, um, and how the parabola either is shifted up, down, left, or right. Again, when our a is a positive value, we consider our vertex in the minimum point. If our a is a negative value, our vertex is considered a maximum point. Now, in this section 2, in this new chapter 2, we have a way to solve for the vertex using a formula. Okay, so if you're ever given the equation in general form in the ax squared plus bx plus c, you can use this formula to find its vertex. So to get the x value of the vertex, you're going to do b divided by 2a, and you take the negative sign of that. Okay, once you have that answer, you plug it back into the function, and you'll get the y value. So this is a way to find the vertex using a formula method. Okay. All right. So a new item that we haven't studied before is called the axis of symmetry. Okay, so we knew that our quadratics, have a y axis symmetry, but now we're able to actually define this by an imaginary line. We can find the equation of the axis of symmetry, and the best way to get this equation is going to be the x value of the vertex, which is given in the formula, right? To get the x value of the vertex is negative b over 2a. So if you're asked in your classes to find the equation of the axis of symmetry, is very easy. It's the x value of the vertex of your parabola, okay? And again, when graphing, when you go into the WebAssign, don't forget to put or to draw the axis of symmetry. And again, it's drawn by a dashed line. All right. So again, what are I guess, one of the pluses of having a quadratic in general form is the just by looking at it, we're able to see what the y-intercept is, right? If x is equal to 0, it gives us what the c value is, which represents the y-intercept. But again, the standard form is a lot easier, especially for graphing. We love the equations when they're in standard form because just by looking at them, we're able to find out what our vertex is, and we're able to sketch the graphs a lot easier. Now, if we need to convert from general form to standard form, it's a process called completing the square. So let's go ahead and practice that. So let's look at this equation here, or function, excuse me. F of x is equal to 4x squared plus 8x plus 16. And we want to write this quadratic function in standard form. So this is the process, and we color coded a little bit so it hopefully it helps out. So the first thing we need to do is, in order for us to complete the square, the a has to be a 1. So in this case, it's not. Our a value is a 4. So what we want to do is we want to factor out that 4 only to our 2x terms. Yes? So the first thing we'll do is we're going to isolate the 4x squared plus 8x, and we're going to factor out that 4. So to factor out that 4, again, we multiply 4 to the parentheses, and it's going to give us um, x squared plus 8 over 4x. Again, we can simplify that, and that's going to give us 4x squared plus 2x plus 16. Okay, so now we can start what's called completing the square. Okay, so here, to complete the square, you're going to take half of b and square it. Okay, so our b value here is 2. We're going to take half of that, so it's dividing by 2. 2 divided by 2 is 1. Now we're going to square it. So 1 squared is 1. So what this value is telling us, that 1 is the value that will make our items inside the parentheses what's called a perfect square. So let's see here. We want to have this 1 in here, but we can't just add the 1 because we want to, or because we want to complete the square. So what we do is we can do plus 1 and minus 1. So what we're really adding is 0, right? We're not changing the equation. We're not unbalancing our equation because we're adding 0. So what we do is we can do a little bit of math manipulation to borrow that positive 1, right? So what we're going to do is we're going to borrow that positive 1, okay, for us to have that perfect square. And a perfect square, if you can see, we wrote it here. This x squared plus 2x plus 1 is represented by x plus 1 times x plus 1. This is what's called a perfect square. Now, let me explain where we got this negative 4. Well, we had added a plus 1 and a minus 1. But if you recall, we had factored out a 4, and we're taking it out of the parentheses. So we have to multiply that 4 back into that negative 1 if we want to get it out of the parentheses. So 4 times the negative 1 is where we get the negative 4. Okay? So now you can see that the x plus 1 times x plus 1, we can rewrite it as x plus 1 squared, and the negative 4 plus the 16 is going to give me the plus 12. So voila, we converted a quadratic function that was in general form into standard form just by doing a simple, factoring technique that's called completing the square. And now I can look at this function and know what the vertex is. This graph got shifted 1 unit to the left, 12 units up. So the vertex is at negative 112. Okay. So again, let's look at another example. Write the quadratic function in standard form and identify the vertex and the axis of symmetry. And again, the axis of symmetry is going to be the easy one. It's just the x value of the vertex. So let's go ahead and do this one again the same way. Um, let's go ahead and just encapsulate the x squared plus 2x. Now on this one, I don't have to factor out anything because my a is already 1. So I don't have to do any extra work. So let's go ahead and complete the square. We're going to take half of b and square it. So 2 divided by 2 is 1. 1 squared is 1. So we have the same process again. We're going to add 1, subtract 1. I'm going to borrow only the positive one and take out the negative one out. Okay, so when I'm using just the positive one, that's going to give me my perfect square, which is going to be x plus 1 squared. And then outside, I had a plus 1 minus the 1 that I had used to complete my square. It's going to give me 0. So now it's in standard form, and I can see that this graph only had a horizontal shift, right? This graph only got shifted 1 unit to the left. So my vertex is negative 1, 0, okay? And again, the axis of symmetry is the easy answer. What is the equation of the axis of symmetry? Well, that's the x value of the vertex. So the answer is going to be x is equal to negative 1. And again, we represent this on the graph as a dashed line. Don't do a solid, it's a dashed. All right. Again, if you have any questions, if I'm going too fast, please let me know. Raise your hand or put a question on the chat. All right, let's go ahead and try this one. F of x is equal to 2x squared plus 8x plus 7. And so if you see and recall on this particular one, we don't have an a, we don't have a value 1 for the a. So we're going to have to factor this out again. So let's go ahead and encapsulate the 2x squared plus 8x only. The first thing we need to do is we're going to need to factor out that 2. Okay, so this is going to give us 2 times x squared plus 4x. Now we're ready to complete the square. So we're going to take half of b, in our case it's 4, and square it. So 4 divided by 2 is 2, and 2 squared is 4. So 4 is a factor that I need to complete the square. So what I'm going to add inside the parentheses is plus 4 minus 4. This is me not changing the problem, not changing the value of the problem, because 4 minus 4 is 0. I'm technically um, adding 0 to this problem, okay? So again, I only want to borrow the positive 4, so I'm going to take that negative 4 outside the parentheses. Hence, I have to give back the 2 that I had factored out originally. So this is going to give me 2 times x squared plus 4x plus 4. 2 times the negative 4 is a negative 8, and I have the plus 7 outside. So I can rewrite this and simplify. The x squared plus 4x plus 4 is that perfect square, which is x plus 2 times x plus 2. Minus 8 plus 7 is the negative 1. And if we write this in our standard form, we're going to get 2 times x plus 2 squared minus 1. So it's in this format. Again, we can tell that our vertex is at negative 2, negative 1. The graph got shifted 2 units to the left, 1 unit down. And our axis of symmetry is the x value of the vertex. Our x value of the vertex is negative 2. So the equation is x equals negative 2. Hopefully easy stuff. All right, let's try one more. Um, let's look at this function, 5x squared plus 15x minus 5. Let's just go through the process. Again, I'm only going to concentrate on the 5x squared plus 15x. A is not 1, so let's make it a 1 by factoring out a 5. All right, let's go ahead and complete the square. Take half of b and square it. Um, you all love fractions, right? So this one's a fraction, so don't be scared. We're gonna add a 9/4 and subtract a 9/4. Okay, so let's go ahead and take out the negative 9/4 out because we don't need it. We're just gonna need to borrow the 9/4. when I take out the negative 9 fourths, again, don't forget to multiply or give back the 5 that we had factored. So negative 9 times a 5 is that negative 45 over 4. Okay. Now, um, x squared plus 3x plus 9 4 is our perfect square. We have x plus 3 halves times x plus 3 halves. Now, to add the fractions outside, we need a common denominator. So we converted the negative 5 into negative 20 over 4. Now we can add those fractions and simplify. So the answer in standard form is 5 times x plus 3 halves squared minus 65 over 4. So here, um, oh, sorry, Yvette, did I see your hand? Did you have a question?
Yeah, Ruben, I just wanted to ask or add something really quick, if
Go
that's
ahead,
okay.
please. Yes.
So whenever you're trying to get the perfect square, if you have a fraction here, it might be kind of crazy, right? But I'll give you a little shortcut. The number you take or the number you get after you take a half, notice we got 3 halves. That's always going to be your number that it goes in the parentheses here. So that's just a little shortcut in case you run into a fraction.
Thank you so much for bringing that up. And I tell my students that all the time too, because sometimes they tell me, "How did you know that was the perfect square?" And that's what I tell them too. I tell them, look at the value before it got squared, and that's the value that makes the perfect square. So thank you for that. Awesome. So finishing up this problem again, our vertex is going to be at negative 3 halves and negative 65 over 4. Again, the equation of our axis of symmetry is the x value of the vertex, which is x is equal to negative 3 halves. Awesome. All right, so let's look at converting the graph into the equation, right? So this one says, write the standard form of the quadratic function whose graph is a parabola before. So if for us to really know how to do these, hopefully by now you guys recognize, one, that this is a parabola and it came from our parent, the quadratic function x squared, right? So the parent is a parabola that has a vertex at the origin. So if we look at this graph, what we see compared to our parent function, this parabola got shifted 1 unit to the left and 1 unit down. So hopefully with this information, we're able to write the function based on what we know using the standard form. The standard form set, given the vertex is hk, so we need at least one additional point to really just um, make sure that we have the right function. So here, what we can see is that we can plug in values into the standard form to get those points. Again, one of the points we can use is always the easy one, the 0, 0. And also, we have a point that's given, right, which is the vertex. Just by looking at it, I knew that the vertex of this parabola was negative 1, 1. Okay. So again, if I plug in these points into my function, I can simplify and it will give me that the a value, okay, which is good to know, is 1. And this was for us to, the reason why we used the point is because we wanted to find out, okay, I know that the graph got shifted, but did the parabola stretch or shrink? And this is a great way to solve, picking a point and solving for the a value. So now that we see that this parabola did not get shrunken or stretched, we can come up with the equation. And we know that, again, this parabola got shifted 1 unit to the left, 1 unit down. And if I put these values, I put the vertex into the formula, it's going to give me x plus 1 squared minus 1. Okay, so the first part is picking a point to see if our parabola either got stretched or shrunk. Yes? All right, let's look at another example. Write the standard form of the quadratic function whose graph passes through the given point with a given vertex. Again, this is a very similar process. To do this, they're giving us a point that they want us to go through. So let's go ahead and use our standard form of the quadratic equation. And let's go ahead and plug in these points. We have the x for 0, y is 3. That's the point that they want the parabola to go through. So let's go ahead and plug it in and simplify. So when we do that, we get a is equal to 2. Okay. So now all we have to do is, now that we have a, we plug in the vertex into the standard form to the h and k and the a for the 2. So 2 times x minus, so minus 3 squared minus 15. Again, a negative times a negative is a positive, which gives us our answer. 2 times x plus 3 squared minus 15. Okay. All right. Now, to solve for the intercepts, okay, there's several ways to solving for the intercepts. One way that we probably had been doing it up till this point was just algebraically. If we wanted to find the x-intercepts, we substitute the y value for 0 and solve for x. But in this new section, they're going to give us a new way to solve for the zeros. And again, different names to finding the zeros of a quadratic. We usually say zeros, or the intercepts. Also, you'll see the computer use the roots or solutions. All these mean the same thing. It's just where the graph crosses the x-axis. Okay. All right. So again, we can use the square root property, but that always can't be used. We can factor, but sometimes we forgot how to factor, or it could be a little bit complicated. But the for sure way that this section is going to teach us that will always work is called the quadratic formula. And hopefully some of you guys remember this from high school, right? So if you ever need to find the x-intercepts and the factoring or the root properties can't help, the quadratic is here to the rescue. It'll always never fail you. Okay, so let's look at the square root property to finding the zeros in this particular example. So we have f of x is equal to x squared minus 4. The square root property is just solving for x algebraically. I'm going to add 4 on both sides. To get rid of the square, I'm going to do the opposite, is by taking the square root. When I take the square root of both sides, the square root of 4 is plus or minus 2. Hence, my x-intercepts are x equals 2 and at x equals negative 2. Now, what we could also do is, again, solving, right? If we have the function on the right, just solving algebraically for the x-intercepts, the quadratic equation is its standard form. Again, we do a little bit of algebra, and we can see that our x-intercepts are at x equals 7 and x equals 1. Okay, but now we have another means, oh, excuse me, let me show you factoring, an example of factoring on how to find the x-intercepts. So let's say that I have x squared minus x minus 6. I have a polynomial that um, I can factor, and what I say to myself, I need two numbers that when I multiply them together give me negative 6, and when I add those same two numbers, give me a negative 1. They give me the value of c and b, right? So those two numbers are negative 3 and 2. So this polynomial factors by x minus 3 times x plus 2. So using my 0 property, the only way that I can get 0 is if x minus 3 is equal to 0 or x plus 2 is equal to 0. So solve for x. So my intercepts are at x equals 3 and x equals negative 2. And I love all these methods because I think they're just fundamental. But again, using the quadratic equation will never fail you. So if I look at the same example, the same polynomial, x squared minus x minus 6, and use the quadratic formula, let's just review the quadratic formula. The quadratic formula is given by this. Negative b plus or minus b squared minus 4ac all over 2a. And again, if they give us a quadratic in standard form, this is an ax squared plus bx plus c. So it's just plugging the values. So in our example, a is 1, b is negative 1, c is negative 6, and we just plug them in to our quadratic formula. And after we do plug it in and do this math, we will see that we get the same answers. X equals, um, let's see here, what do we do here? Why are they not the same answers? Am I not picking? Oh, sorry. It's not the same answers because it's not the same problem. Excuse me. I'm looking to solve a different polynomial. Didn't see right here. X squared minus 2x minus 8. Excuse me. So this is the one that I'm picking. A is 1. Sorry. B is negative 2. C is negative 8. And when I plug it in, these are its x-intercepts. The x-intercepts are x equals 4 and x equals -2. Again, our quadratic formula, if any of the other techniques seem too complicated or don't work, our quadratic formula will always work. Okay. All right, let's see. Let's skip. Let's go to section 2.2. All right, so graphs of polynomial functions. Okay, so what is a polynomial? Well, a polynomial is an expression that has more than one term, right? That's where the polynomial comes from. Poly means many, nomial means numbers or many terms, right? Um, Also, the way we like to think of polynomials and the graphs is that they're continuous, right? That they told us back in high school that I can draw the graph without lifting my pencil. If I can draw the graph without lifting my pencil, then I'm dealing with a polynomial. The one on the right, if you see, I would have to lift my pencil to start one and to finish the other, right? So the one on the right is not a polynomial because there's a break, okay? Um, Now, um, how about these? Okay, are these polynomials? So if I see here on the one on the left, okay, it is a polynomial. I can draw my graph with one process without lifting my pencil, but there's another point for polynomials. You know, we cannot have sharp turns. You know, when we're drawing polynomials, it has to have only smooth curves. So the one on the right, since it has um, a sharp turn is not a polynomial. Okay. So what we want to teach you in or show you in the second section is that we can look at the end behavior of polynomials in order to get a better understanding of what these graphs are going to look like and to help us graph. Okay, so let's first look at the first one. If you look at the first one, we are looking at a quadratic function, but what you want to look at is the degree always. The degree of the function will tell you a lot of information. So if the degree of a function is even, okay, and the leading coefficient is a positive. And let me also give a little bit more explanation about it as far as the degree. Again, remember the degree is the highest exponent. So in a quadratic, our exponent, the highest exponent is 2, and 2 is an even number. So hence, this is an even function. So our a value, if our a value is positive, okay, our graph will always be pointing up in both directions, okay, both on the left and to the right. If you look at the second graph where our parabola had a reflection on the x-axis, our a value is negative, but because our graph is an even function, the graph will be pointing down both on the left and on the right. And this is what's called our 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 end behavior or left and right hand behavior. Okay, so that's for any even function. They're gonna you can apply this concept. Now, if our function is not even, we can think of our other side of our coin is odd functions. An odd function is any function that has a degree with an odd number. So as an example, we look at our cubic function, right? So our cube function is an odd function because its degree is 3. 3 is an odd number. And we follow kind of the same process for our end behavior. If our A is positive, I always think of if A is positive, our graph is always increasing. So it's small from the bottom and it's growing, going up to the right. But the way you want to think about it for your homework, when they ask you what is the end behavior, you can see that on an odd function, when A is positive, the left is going down and the right is going up. Okay, so that's one way to think about it. Another way. Now, if we have a function that is odd, but our A is negative, our end behavior is going to flip. It's going to be going up on the left and going down on the right. And like I said, I like to think of when it has a negative um, um, function, it's decreasing, right? It's going from large number to a small number. Okay, so this is what's called our end behavior. So let's look at an example or several examples here. So the first thing again that we need to look at before we can describe our left hand and right hand behavior is we need to know the degree of the polynomial and whether that degree is an even number or an odd number. So if we look at A, we see that our highest exponent is 8. So 8 is an even number. So since it's an even number, I know that it's either going to be pointing up or pointing down on left and right. So to determine that, I have to look at the leading coefficient. The leading coefficient of this polynomial or of this degree 8 is 3. 3 is a positive number. So hence, the left-hand and right-hand behavior of this function is going to be going up on the left and going up on the right. On both sides, it's going up. Okay. So if we look at, again, our formulas here, again, we're dealing with an even function, and it's going to be our behavior is going to be going up on both sides. Yes? All right, so let's look at our B. The highest exponent that we have is a 3, so our degree of this polynomial is um, a cubic function, and this is an odd function. Now, our leading coefficient is a negative number. So if we look at our formula sheet for an odd function that has a leading coefficient of a negative, it's going to be increasing from the left and decreasing from the right. Those are left-hand and right-hand behavior, right? Um, let's look at C. Um, what is the highest exponent that we see? Our highest exponent is the 8. So our polynomial or our function is an even. Our leading coefficient is a -4. So that means that both on the left and right hand behavior, the graph is pointing downwards, right? So both left and right is going down. All right, let's look at the last one, D. Okay, on D, our degree of this polynomial is a 3, right? But be careful, they had factor out a -2 to the three terms inside. So technically, if I give that -2 back, the leading coefficient of that x cubed is a -2. So my leading coefficient is negative. So now we're dealing with an odd function with a negative as a leading coefficient. So that means that it's going to be our left-hand behavior for D is going to be rising from the left and going down from the right. Yes? And it's our last example here from our formula. Okay? Any questions? Very good. All right, let's move on. Um, so let's look at these graphs to determine how the graphs are crossing the x-axis and what does this mean and how we interpret this when we're finding zeros. So as we had mentioned to you, when we're finding the x-intercepts, another representation of this is in graphs is where is the graph crossing the x-axis? That's what our x-intercepts are, right? So as you can see in this first one in the screen, it's an orange and purple. We did the bold circles, right? We're showing where it's crossing the x-axis. So these are the zeros. So we can look at the graph. So on the first one, on the green one, we're crossing the x-axis at -1, 2, and 4, right? On um, the orange is kind of special. Um, on the first one, it's just touching that, right? But guess what? This one, when the graph touches, what that means is we have a double zero here, or we call this double multiplicity. And we're going to cover this, okay? And if we did it algebraically, it's going to give us two answers for x equals -2. And whenever you get that, you know that that point is only touching the graph. It's not crossing it, but touching it. Okay, as you can see, we only have one value for x equals 2, so that's just crossing the graph. And if we look at the purple, we have the same thing going on. We have zeros at -2, 0, and 2, but at the origin, we have a double zero. We have a double multiplicity, and if we did it algebraically, you could see it, that you're going to have two answers for x values for 0. Okay. All right, so I had mentioned that word already, so I was getting ahead of myself. So let me give you this definition of multiplicity of the zeros. The multiplicity of zeros is to determine whether the graph is going to cross the x-axis or just touch it, okay? So let's see here. If we're looking at my parent function, the quadratic function, do you see that my 0 just touches the origin, right? But this one has a double 0, right? If I would look at it mathematically, x times x, okay, I have two zeros, 0 at x and 0 at x. So that's why it has two zeros, okay? Now, the graph at, will only touch and turn at this point, okay? If we look at the cube function, the cube function has the same situation. It has three x's being multiplied to each other. So again, at this graph, it does cross it, but it's kind of like um, crossing at 2 points, but this is what's called an odd um, crossing, and we'll cover that as well. Okay, but you can see it algebraically that we have three zeros as well. And that's one of the things that I tell my students. The degree of the polynomial will also determine what's the maximum number of zeros that a graph may have. Okay. All right, so let's look at this example. Find all the real zeros and determine the multiplicity of each zero. So we have x squared minus 2x plus 1. So for me, the best way to solve it, again, you can factor it, but let's practice using our quadratic methods, right? So let's do factoring. That's my go-to. So let's factor x squared minus 2x plus 1 to find the zeros of this. So again, I need to find two numbers that when I multiply them together give me 1, and when I add the same two numbers gives me the negative 2. The two numbers are negative 1 and negative 1. So this factors as x minus 1 and x minus 1. This is a perfect square. So if you see here, when we're solving for this, we have two answers for one. So that means that this graph is going to touch twice at this point. At x equals 1, it's only going to touch and not cross. So if we were to draw it, okay, this graph got shifted 1 unit to the right, but it's only touching, right? Touching it and going back. So therefore, this happened twice. It's an even, right? It's an even touch. So it's an even multiplicity, okay? All right, let's look at this one. Find all the real zeros and determine the multiplicity of each zero, okay? So one of the first things that I would do, since I see that in this function, there's a t in each of the three terms, let's factor out the t and to help us out. So the first thing that I would do is I would factor out a t squared. That's the smallest t that I can take out. And when I do that, I'm left awesome with a quadratic, t squared minus t minus 30. Then what I can do is, again, apply one of my factoring techniques. T squared minus t minus 30 factors into t minus 6 times t plus 5. So I have possibly just by looking at three zeros, but it should have four, right? Because the degree of this polynomial is 4. Let's look. So using our zero property, t squared could equal to 0, or t minus 6 is equal to 0, or t plus 5 equal to 0. So solving for t, okay, we see that if I take the square root of 0, this is what we're going to have two zeros here, right? So at t equals 0, we have an even multiplicity because we're going to have the answer twice, okay? There's two of them, so it's an even. And also this means that the graph is only going to touch at that point, okay? So at t equals 6, it only happens once, so it's an odd. Um, and at t negative 5, this only occurs once, so this is an odd multiplicity, okay? Because they're crossing the graph only once, okay? All right, so, and if we were to graph, again, we can use what we have learned now. We can look at our um, points where this graph should be crossing the x-axis. We could also apply our left hand and right hand behavior in order for us to get a little idea of how the graph is going to work. Again, this is a degree 4, so it's an even polynomial. So that means that the graph, because our leading coefficient is a positive value, is going to be pointing up on both sides. Now, if we really wanted to be very specific, then we can also do a table to get more points. again, to go ahead and, to get more points to draw this graph. But again, most of the questions that you'll see on WebAssign for these problems are multiple choice. And with all this information, very easy to determine the graphs of these, okay? All right, let's move forward. So let's sketch the graph. Let's sketch the graph of x cubed minus 3x squared. Again, the first thing that I would do to help me graph is, again, do a little key. Let's see what the end behavior is. Let's find the zeros, identify multiplicities of each zero, find the y-intercept, and plot some additional points. So let's go ahead and do that. Let's start with our end behavior, identifying our end behavior. So I see that this is an odd function because our degree is 3. Our leading coefficient is a positive. So that means that this graph is going down on the left and rising on the right, right? So that's our left-hand behavior. Um, let's find the zeros. Let's find the x-intercept. So I would factor out an x squared. So our zeros are at 0 and at positive 3. But I see that we have a multiplicity of 2, or even multiplicity for that 0, right? The square root of 0 is either 0 or 0, right? So, and then 3 is just 1, right? It's an odd. What about our y-intercept? Can we find out what our y-intercept is? So hopefully it's easy to see that there's if x is equal to 0, we end up with 0, right? So we have our y-intercept at 0, 0. Um, let's go ahead and start graphing, okay? So let's start with our points that we have discovered. We have a double 0 at our origin. We have the equation that crosses at positive 3. We know that this graph is going to um, go down on the left and rise on the right. So if we want to get a little bit more detailed, this is what we know so far. We can get additional points to see what's going on between 0 and 1, right? So we can pick some values. Let's see, these additional values, I picked a 1 and 2 just to get a better idea as far as what's going on. So when x is equal to 1, y is equal to negative 2. When x is equal to 2, y is equal to negative 4. And I wanted it to get a little bit more detailed, so I picked x equals 2.5 to see what, the y value was going to give me. Again, and if I would roughly sketch these points, this was what my parabola, or my cubic function would look like, right? But again, hopefully with a graphing tool, you can see that our graph is a lot easier. But again, this is good to see what our graph is going to look like and determine on our homework what our graph should be, okay? All right, so again, this is the actual graph from a graphing tool, just much prettier, not all these squiggly lines, right? So again, this is what our graph would look like if I used a graphing tool. All right, let's move forward. Let's introduce synthetic division, okay? So a synthetic and complex division. All right, so let's look at this problem. F of x, or this function, f of x is equal to 6x cubed minus 19x squared plus 16x minus 4, okay? We can factor this, and by us factoring it, we can find where our zeros occur. But sometimes it could be very, very hard to factor a number like this, or it can be complicated. So what we're going to help you is how to reduce a polynomial in order for us to have a better function to factor or even get the zeros, okay? And we're going to do that by using division. And one format is called long division, and this is kind of the way the name says it all. It's kind of straightforward. Is using the polynomials how they are, and then we'll show you a shortcut method which is called synthetic division. Okay, so the first steps in order to do long division, we need to assure that this is going on. First, we need to arrange the terms that are being divided in descending order, and if any any exponent or any term is missing, we're going to add 0 to it, okay? We're going to fill in the gaps, okay? We cannot have any gaps, and our polynomial has to be in descending order. Then number 2, we then just divide. Now, before I do this, let me review a little bit of division, just regular division, just to show you that we're doing the same thing. So let's say that I want to divide 2 into 124, okay? The way you do regular division, okay, you say, can 2 go into 1? No. But can 2 go into 12? Yes. So you say, what number can I multiply to 2 to get close to 12? And then you say, well, it's 6. So you multiply 6 times 2 is 12, and then you subtract. We subtract these two numbers. 12 minus 12 is 0. Then we bring down our next term, which would be 4. And then I say, is there a number that I can multiply to 2 to get 4? Yeah, that's 2. So 2 times 2 is 4, and 4 minus 4 is 0. So 2 divided into 124 gives me 62. So this is just an example of how we do regular division. But believe it or not, this is the same process that we're going to do to divide using long division using polynomials. Okay, so what I just explained to you is just this multiplying and dividing, multiplying and subtracting process. So let's go ahead. Let me go ahead and show you all this. Again, these slides will be available for you at the end, okay? So let's use long division to divide these two polynomials. So 20x cubed minus 35x squared plus 23x minus 6. Okay, I'm going to divide this number by this polynomial, 4x minus 3. So this is my divisor, this is my dividend, okay? So I like to divide old-fashionedly by doing that little house that I drew earlier. Okay, I'm going to put my divisor outside, 4x minus 3. I'm going to divide it into this polynomial, 20x cubed minus 35x squared plus 23x minus 6. And I go through that same process. Can 4x minus 3 go into just 20x cubed? No. But the 4x minus 3 can go into these two terms. So then I say, what number or what term can I multiply to 4x to get a 20x cubed? Well, that is a 5x squared. So, and I can show you here by the division, right? If I multiply 5x squared to 4x, that's going to give me the 20x cubed. So that's what I'm going to do. I am going to multiply that 5x squared to the to the 4x minus 3. And that's going to give me 20x cubed times 5x squared times a minus 3 is a minus 15x squared. What comes next after division? I subtract. So minus 35x squared minus 15x, that's going to give me the 20x squared. The 20x cubed minus 20x cubed cancels out as 0, right? Then I bring down my next term, the plus 23x. Then I start the process again. What number can I multiply to, or what term can I multiply to 4x to get a negative 20x squared? Well, that would be a negative 5x, right? So if I multiply a negative 5x, I'm going to get negative 5x times 4x is a negative 20x squared. Negative 5x times a negative 3 is a positive 15x. Subtract. Now, if you see, we've been putting parentheses because with the subtraction, since we're dealing with a polynomial, please don't forget to distribute that negative sign. A negative times a negative is a positive. A negative times a positive is a negative. So 20x squared plus 20x squared is going to give me 0. 23x minus 15x is going to give me 8x. Then I bring down my last term, the minus 6. And then I say to myself, what can I multiply to 4x to get a 8x? Well, that's the 2. That's going to give me 8x minus 6. Subtract, distribute the sign. It's going to be minus 8x plus 6. And when I add them together, gives me 0. So this value here is the quotient. So when I divided these two numbers, if you see, we went from a cubic function to a quadratic function. So if I wanted to find the zeros, now I can factor it, use a quadratic equation, or use other factoring techniques to find the zeros, and it's not so complicated. We don't have this scary number, and using division will help us reduce these polynomials. Okay, I've got 9 minutes left. Again, let's go through some of just terminology of the division. Again, the number outside is called a divisor. My answer is called a quotient. And whatever is left over, in our case, it was 0, and we always want to have a remainder of 0. We love it. This is called our remainder, okay, what was left over. So let me go ahead and show you how, if you ever happen to have not 0 as a remainder, give you the syntax on how to write the remainder. So whenever, if you have a number here, you can also write it by adding a plus. Plus is like having a decimal, right? If you had a plus, means you had a remainder. 0, the remainder, divided by the divisor. Okay, so our divisor is 4x plus 3. So the answer, if we had to include the remainder part, would be like this: the plus 0 over 4x minus 3. Okay, let's see. Do we have time to do synthetic division really quick? Let's go ahead and show you. That was long division. Now let me show you a quicker way to do the division, and it's called synthetic division. And you would have to follow these terms. Now again, you can find this on our YouTube channel. So let's just go directly to the example, just to show you how this works. Oops. So here, I want to use synthetic division to divide x squared plus 5x plus 6, and I'm going to divide it by this polynomial x minus 1. Okay, so this one value is going to be my k, and when I'm using synthetic division, I'm only using the coefficients of the polynomial. But just like long division, I got to make sure that they're in descending order and that there aren't any gaps. I have a placement for all. So I have an x squared, I have an x, and I have a constant. So the coefficients are 1, 5, and 6. Again, I'm dividing by this k value, which is 1. And the way I do synthetic division is this way. I bring down the 1, okay? Then you're going to multiply 1 times 1. 1 times 1 is 1. And then you're going to add 5 plus 1 is 6. Okay, and then you do it again. 1 times 6 is 6. So 6 plus 6 is 12. So in this problem, okay, we don't have a remainder of 0. So when I can represent, this is the quotient. The quotient is going to be 1 degree less than what we started. So we started with an x squared. So our final answer, or our quotient, let me go to it because I'm giving you a lot of the syntax. Our answer would be, our 1 now is an x, 6 becomes our constant. And again, we had a remainder, so the way we represent the remainder is plus the remainder over the divisor. Our divisor was x minus 1, so it's x minus 1. Okay, so I still got about 6 more minutes. Let's see, can we sneak one more in? Yes, let's go ahead and sneak one more in. Let's do synthetic division to do this one. Again, here my k value is going to be the 8. I have a degree 3 polynomial, and I have a placement for all, and they're already in descending order. I have a 3, 2, 1 constant. Let's go ahead and do synthetic division. So I do my little house. My k is my 8 value. My coefficients are 4, 36, 36, and negative 2. So let's start. I bring down the 4. 8 times 4 is 32. 36 plus 32 is going to give me 68. Then I multiply again. 8 times 68 is going to give me 544. I'm going to add 36 to 544. That is going to give me 580. Multiply 8 times 580. That's going to give me 4,640. So I'm going to subtract or add negative 32 plus 4640. And that's going to give me 4608. So this was my remainder. Again, I started with a Q function, so the quotient is going to be a quadratic. The answer is going to be 4x squared plus 68x plus 580. I had a remainder plus 4608 over x minus 8. Again, We do have a lot more. Again, we are in the summer. We're trying to cover as much information for you as possible since we are going pretty fast, especially for all of those of you who are taking a summer one class. So keep in mind that we record these and you can find these on the YouTube channel and all the slides will be in there. Ms. Chuka, do you have any last minute words for our students?
I just encourage you all to look at the YouTube channel, because if you go back to the spring session recordings, you can find more recordings that cover the rest of these slides as well. And then if you would like a copy of the PowerPoint, send me an email and I'll send it to you.
Thank you. Awesome. Again, thank you all for joining us on a Friday. Please continue joining us. Again, if you know someone that missed it, please look at our YouTube channels. You'll find our recordings there. Thank you again, all.
Thank you, Mr. Carrizales and Ms. Chuka, for your presentation. We do want to remind you all about our previously recorded sessions, which are available on a YouTube playlist. This session will also be available on that playlist later today. Also linked is a short survey to help us improve our TVE sessions. Please take a few minutes to fill out that survey and remember to send your student ID number to Ms. Patricia. She sent individual messages to everyone to sign you all in. Before you all leave, I want to share the TVE sessions that we will have next Friday. There we go. So for next Friday, for 1314, we will be covering exponential and logarithmic functions and properties. And for 1324, they'll be covering simple and compound interest, annuities, and systems of equations. Thank you all for coming in today. We hope you all have a lovely weekend. If anybody has any questions, feel free to use the chat box or your mic. We hope to see everyone again next week.